Welcome to the Journey Chez Chem. Today's warm-up is review from yesterday's assignment. I'm sure you can do it. Give it your best shot, and I'll see you in a moment. In number 1, we have one of the decompositions, lithium chlorate. And whenever we decompose a metallic chlorate, we always get lithium chloride, a metal chloride, and oxygen gas. And we did something very similar to this in one of our labs. Now I write what I am given in the problem, 23.5 grams of the lithium chlorate, and what I'm trying to find is oxygen, and also sometimes I write there the unit that I'm looking for so that I don't have to continually go back to the original problem. Well, the first thing I do is get my balanced equation, and I have 3 oxygens on one side and 2 oxygens on the other side. Therefore, the common multiple between 3 and 2 is 6. So I need 3 oxygens and 2 lithium chlorates. Once my formulas are written, I cannot add subscripts. I can only add coefficients. Then I take my 23.5 grams of the lithium chlorate and I change that to moles. And because I have grams, I need the AMU. And lithium is 6.9. And chlorine is 35.5. And I have 3 oxygens, and 3 oxygens is 3 times 16.0. 6.9 plus 35.5 plus 48 equals 90.4 AMU, or grams per mole. So 1 mole of the lithium chlorate is 90.4 grams lithium chlorate. Then once I have my moles, I use my mole ratio from the balanced equation. And there are 3 moles of oxygen for every 2 moles of lithium chlorate. And then from moles, I'm going to change to volume. And I know that 1 mole of any gas, including oxygen, under standard conditions, is 22.4 decimeters cubed. Now, we also know that 1 liter is equal to 1 decimeter cubed. So in this case, I want to use decimeters cubed because I'm going to centimeters cubed. And therefore, I need one more step. I need my centimeter cubed in the top and my decimeters cubed in the bottom. And I know there are 10 centimeters is equal to 1 decimeter. Therefore, if I cube 10, I get 1,000 centimeters cubed is equal to 1 decimeter cubed. Now remember, when I do a problem like this, I take the 23.5 grams divided by 90.4 equals, times 3 equals, divided by 2 equals, times 22.4 equals, times 1,000 equals. And this number comes out to be 8734.5132. I look back to my original problem and there's only 1 number, and therefore I am going to have 3 significant digits. The 4 does not round the 3 up, and therefore my final answer is 8730 centimeters cubed of oxygen. And that's how you do number 1. In number 2, we are needing to get the equation for the synthesis of ammonia from its elements. And then I write down what am I given in the problem and what am I solving for. And I also write the unit so that I can see where I'm going. Well, I have 107.4 grams of nitrogen. Ooh, nice long conversion factor there. And 1 mole of nitrogen is 28.0 grams of nitrogen. And nitrogen's diatomic, and each atom is 14.0 times 2 gives me the 28.0 grams. Now notice my grams must cancel, and conversion factors can help you to go in the right direction because they will show you right away. If I put volume here, I could see that it would not cancel. Then I use my mole ratio. I'm looking for ammonia, and I want to cancel nitrogen. And from there I go to volume. There are 22.4 decimeters cubed of ammonia in every 1 mole of ammonia. In this case, we're talking ammonia, but it could be any gas. And then I also know there are 10 decimeters in 1 meter, and therefore if I cube 10, I get 1,000 decimeters cubed is equal to 1 meter cubed. Now again, remember, you must take your original number divided by 28 equals, times 2 equals, times 22.4 equals, divided by 1,000 equals. And the number here comes out to be 17184, and even though normally I would take it 4 places past the decimal and cut it off, I need this 4th digit to see if I'm going to round that 8 up or not. And as you can see, I'm not going to round that up. I need 4 significant digits in my answer. And therefore my answer is 0.1718 meters cubed of ammonia, or 1.718 times 10 to the negative 1 meters cubed of ammonia. Either answer is fine. And that's how you do number 2. Let's talk about volume. Now, primarily the importance of understanding this is, again, we talk about standard molar volume. And standard molar volume is that 22.4 liters or 22.4 decimeters cubed is equal to 1 mole of any gas under standard conditions, which would be standard temperature and standard pressure. Now, that is how we make conversions. And if we're given an initial volume and we need to change it to moles, we would have to use standard molar volume. That's the only difference at this point. And so it's mostly to have students understand that if you have grams, that you use the gram formula mass or the AMU, and when you have volume, you must use standard volume. And therefore, let's say, for example, that we're synthesizing water. Well, water is hydrogen gas plus oxygen gas, and we get water. Now, as always, I have to balance my equation. And I have 2 oxygens, therefore I must put a 2 coefficient, and then I must also have 2 hydrogens. Now, say, for example, we are given 3.0 decimeters cubed of the hydrogen, and I want to know what volume of water in meters cubed. At this point, the conversion factors become extremely important. Now, I have 3.0 decimeters cubed of my hydrogen. No, I want that to be my oxygen. I just wrote it by the wrong element or diatomic molecule. So we want to start with 3.0 decimeters cubed of oxygen. Now, in order to convert my decimeters cubed, I need a decimeter cube type of unit. I need a cubic unit. And therefore, I know that 1 mole of any gas is 22.4 decimeters cubed of that gas under standard conditions. And then, just as I did before, I'm going to use the mole ratio to change compounds. And I'm going to water, so there are 2 moles of water for every 1 mole of oxygen. And then to get back to volume, again, I'm going to use my standard molar volume. And because these conversion factors, this value is equal to this value, I can use them in either direction, just like we've always done in conversion factors. And therefore, 1 mole of water, vapor, is 22.4 decimeters cubed of water. And that's how I get my moles to cancel and I get back to a volume. And then I want my volume to be in meters cubed, and therefore meters cubed will go in the top and decimeters cubed in the bottom. And there are 1,000 decimeters cubed for every 1 meter cubed. Now you can see here that these decimeters cubed cancel, and that's okay. It's important to see the process of what's going on because we're learning to walk. And once we learn how to walk, then we can run. But it's very important to see the process of what's going on. And I like seeing all of the parts of the problem. Now, I can do this in my head, and you can do it in your head too. You have 3 times 2 is 6, divided by 1,000. So 6 divided by 1,000 is 0.006 meters cubed of water. And I have 2 significant digits there. Therefore, I'm going to have to write 0.0060 meters cubed of water in order to get the right number of significant digits, because my final answer must always have the correct number of significant digits as based in the problem. And here I had 2, therefore my answer must have 2. There are only 2 significant digits here because there's a 0 preceding the decimal. If there was a 1 or any regular digit, 1 through 9, in front of that decimal, then they all become significant. And we're constantly reviewing the significant digit rules, and I'm sure you're getting really good at that. And that is a volume. We started with volume and we ended with volume. And the critical point here is that 1 mole is equal to 22.4 decimeters cubed, or liters, at standard conditions only. And that's how you do those volume problems. And today I'm sure you'll review the answers of last night's assignment with your facilitator. And that was some fun, and thanks for being here, and I can't wait to see you tomorrow.